Welcome to the full video lecture on chi-square tests. The content covered in this video is covered in Chapter 7 of the Lock 5 textbook. Before we begin, I want to go to Minitab Express to do a quick review. We'll look at how to construct a frequency table, a two-way contingency table, and a probability distribution plot. Here I have an existing data set. The first thing that I want to demonstrate is how to construct a frequency table. I'll go to Statistics, Summary Statistics, Tally. Here, I can choose a variable. For this example, we'll look at biological sex. The default is just to give you the counts. We can also select percents, click OK, and here we have our frequency table. Frequency tables are used to summarize data from one categorical variable. Next, we'll construct a two-way contingency table. This is used to display data from two categorical variables. Again, I'll go to Statistics, this time Tables, and Cross-Tabulation and Chi-Square. Let's construct a contingency table for biological sex and winter sport. These are two variables that we'll look at later in this video as well. Under display, we can choose to show percent of row totals, percent of column totals, percent of overall totals. These options below we'll see later when we conduct a chi-square test. We click OK and we have our two-way contingency table. In each of these cells, we have the count, the percent for that row, the percent for that column, and the percent for the overall total. The last thing that I want to review with you is how to construct a probability distribution plot. You've seen these already for the Z distribution, T distributions, and F distributions. This week, you'll be introduced to the chi-square distribution. We'll go to Statistics, Probability Distributions, Distribution Plot, and we'll display a probability. This week, you'll be working with chi-square distributions. And when we learn about the two different tests this week, you'll see how the degrees of freedom are computed for each. For this example, I'll just say 3 degrees of freedom. When we're conducting a hypothesis test, we have a specified x value. Chi-square tests, like the F tests, are always going to be right-tailed. The x value then would be the test statistic that you would put in. Just for this demonstration, I'll say 2.5. And this will give us a chi-square distribution plot, 3 degrees of freedom, test statistic of chi-squared equals 2.5, and the p-value is the red area, 0.475291. And we'll see some more examples of this as we move on to conduct that chi-square goodness of fit test and chi-square test of independence. Let's go back now to look at our learning objectives for this lesson. We have 4 learning objectives. First, we'll identify research questions that may be addressed using a chi-square goodness of fit test or a chi-square test of independence. Second, conduct a chi-square goodness of fit test. Third, conduct a chi-square test of independence. And fourth, calculate and interpret relative risk. Let's begin with this first learning objective. Identify research questions that may be addressed using a chi-square goodness of fit test or a chi-square test of independence. A goodness of fit test is used when we have one categorical variable with more than 2 categories. Note that a goodness of fit test with just 2 levels is equivalent to a 1 sample proportion Z test. So what makes this different from the 1 sample proportion Z test that you've done in previous lessons is that now that categorical variable can have more than 2 categories or more than 2 levels. The chi-square test of independence then is when we have two or more categorical variables with two or more categories each. The test of independence looks for a relationship between those two or more variables. Or more is in brackets here because in this course, we're only going to be looking at examples with exactly two categorical variables. Let's walk through a few examples. There are 5 different flavors of runts: banana, orange, strawberry, green apple, and grape. We want to know if the distribution of these 5 flavors is unequal. Our variable, or variables in this case, we just have one, and that is the flavor of runt. That variable has 5 different levels. We would conduct a chi-square goodness of fit test because we have one categorical variable with multiple levels. We have data from a random sample of Penn State students' genders and racial identities. We want to know if there's evidence of a relationship between these two variables in the population. In this example, we have 2 variables, gender identity and racial identity. If we're looking for evidence of a relationship between 2 categorical variables, we conduct a chi-square test of independence. We have a 6-sided die and want to know if there is evidence that the die is unevenly weighted. Here we have one variable, the result of the roll, and that variable has 6 different levels. We could roll 1, 2, 3, 4, 5, or 6. We would conduct a chi-square goodness of fit test to address this research question. Let's move on to learning objective 2, conduct a chi-square goodness of fit test. A chi-square goodness of fit test is used to compare proportions when we have one categorical variable with more than 2 levels. An assumption of this test is that each case may only appear in one category. We're going to be using the 5-step hypothesis testing procedure that you've seen before in the past. Now I'll walk through these 5 steps with you, and then we'll do a few examples. Step 1 is to check assumptions and write hypotheses. All categories must be mutually exclusive. Like I said earlier, each case can only appear in one category. All expected counts must be at least 5. This is the formula for computing an expected count. Each level of that categorical variable is going to have an expected count, and that's equal to n times p, where n is the total or overall sample size, and this p is the hypothesized proportion for that particular group. So we'll have to compute an expected count for every level of that categorical variable. Once we know that these assumptions are met, we can write our hypotheses. The null hypothesis specifies all hypothesized population proportions. The alternative hypothesis is that at least one value in the null is not as specified. Step 2, compute the test statistic. This is the formula for our chi-square test statistic. The observed value here is the actual count in our sample, and the expected count is the same expected count that we checked in step 1 when checking that all expected counts were at least 5. Step 3, determine the p-value. This is when you'll need to go to Minitab Express to construct a chi-square distribution. That will have k minus 1 degrees of freedom, where k is the number of categories. So, for example, with the runts example that we saw earlier, there were 5 different flavors, so there would be 5 minus 1, or 4 degrees of freedom for that chi-square test. This is what the chi-square distribution looks like. Like the T and the F distributions, it's going to look different depending on the degrees of freedom. It's always going to be a right tail test. Step 4, make a decision. You've seen these before. If p is greater than 0.05, we fail to reject the null hypothesis. If p is less than or equal to 0.05, we reject the null. The 0.05 here is that standard alpha level. Step 5, state a real-world conclusion. This is where you'd go back to the original research question and state whether or not there's evidence that the proportions are different from hypothesized. Let's look at an example now. Here's our scenario. We are playing a game with a 4-sided die and want to know if there is evidence that the die is unfair. We roll it 40 times and collect the following data. We rolled a 1 13 times. We rolled a 2 8 times, a 3 11 times, and a 4 8 times. The first step of the 5-step hypothesis testing procedure is to check assumptions and write hypotheses. We're going to be conducting a chi-square goodness of fit test here because we have one categorical variable with more than 2 levels. The first assumption of the goodness of fit test is that all categories must be mutually exclusive. This assumption is met because every time we roll the die, we get 1, 2, 3, or 4. Each roll will fit into one and only one of these categories. The second assumption is that all expected counts must be at least 5. We'll come back to this after we write our hypotheses, because our null hypothesis is going to tell us the proportion that we need to compute these expected counts. We want to know if the die is unfair. If the die is unfair, then the proportions are not equal across the 4 possible outcomes. The null hypothesis then is that the die is fair and that the proportions are equal across the 4 outcomes. Now that we have our hypothesized proportion for each category, we can go back to compute those expected counts. Here's our formula for computing expected counts. It's going to be n, which is the total sample size, in this case 40, times p sub I, which is the hypothesized proportion of the ith group. In this case, groups 1, 2, 3, and 4 all have a hypothesized proportion of 0.25. This means that all of our expected counts, or all of our n times p, equal 40 times 0.25, which equals 10. This is at least 5, so this assumption has been met. Step 2 is to compute the test statistic. Here's our formula for the chi-square test statistic. Observed minus expected squared divided by expected. The summation tells us to do this for each of the 4 possible outcomes. Our expected counts, or n times p, we found in step 1 to all be equal to 10. We plug these values into our formula, and we get chi-square equals 13 minus 10 squared divided by 10 plus 8 minus 10 squared divided by 10 plus 11 minus 10 squared divided by 10 plus 8 minus 10 squared divided by 10. When you're doing this math out, note that all of these fractions are going to be positive because in the numerator, any number that is squared is a positive number. When we do out this math, we get a chi-square test statistic of 1.80. Step 3, we're going to determine the p-value. In order to do this, we're going to go to Minitab Express to construct a chi-square distribution. The degrees of freedom are equal to k minus 1, where k is the number of possible outcomes. Here we have 4 possible outcomes, and 4 minus 1 gives us 3 degrees of freedom. Let's go to Minitab Express to construct a chi-square distribution with 3 degrees of freedom to find the area beyond a test statistic of 1.80. I'm going to construct a probability distribution plot to display a probability. We have a chi-square distribution with 3 degrees of freedom. Our chi-square test statistic is a specified x value. Recall, chi-square tests are always going to be right-tailed, and our chi-square test statistic was 1.80. This gives us a p-value of 0.614935. Step 4 is to make a decision. Our p-value was greater than 0.05, which is the standard alpha level, so we fail to reject the null hypothesis. Step 5, state a real-world conclusion. We failed to reject the null hypothesis, so there is not evidence that the die is unfair. In other words, there is not evidence that any of the probabilities are different from 0.25. Now I want to take you back to Minitab Express to show you how this test could be run there. In step 1, you'll still have to write the hypotheses and check the first assumption by yourself, but you'll see when we run the chi-square test in Minitab Express, it will give us those expected counts, so we don't need to do that step by hand. We'll go to Minitab Express now, and we'll enter the numbers from this table into a blank Minitab Express worksheet. We'll enter this as summarized data. The first column, I'll have the outcome, so whether we rolled 1, 2, 3, or 4. And the second column, we'll have our frequencies. We rolled a 1 13 times. We rolled a 2 8 times. We rolled a 3 11 times. And we rolled a 4 8 times. Now if we go to statistics, tables, chi-square goodness of fit, the default here is categorical data in a column. This means that you would have all of the raw data. In this case, we entered summarized data. The observed counts were our frequencies, and the category names were our outcomes. The default test is a null hypothesis where the proportions are all equal. That is what we have in this case. It is also possible in Minitab Express to run a goodness of fit test where the proportions are not all equal, and in that case, you would specify your own proportions. When I click OK, we'll get our output. In this first table, we have our data summarized in the first 2 columns, the test proportion, or P sub I, the expected count, which is our total sample size times P sub I, and the contribution to the chi-square test statistic. When we were doing this out by hand, that contribution to the chi-square test statistic would be the observed minus expected count squared divided by the expected count for that particular cell. In the second table, we have our total sample size, degrees of freedom, our chi-square test statistic, and our p-value. And we can see that these values are all the same as what we got when we did this test by hand. We can use the values in this table to finish walking through that 5-step hypothesis testing procedure. For step 2, we can get our chi-square test statistic, along with our degrees of freedom, which are often presented in parentheses. Step 3, we can get our p-value. And then in step 4, again, we would fail to reject because our p-value is greater than the standard alpha level of 0.05. And in step 5, there's not evidence that the die is unfair. Let's move on now to conducting chi-square tests of independence. These are used to test for a relationship between 2 or more categorical variables. In this course, we're only going to be looking at cases with 2 categorical variables. Each variable can have 2 or more categories. Data are displayed in a contingency table. Each case can appear in only one cell. Again, we'll be using the 5-step hypothesis testing procedure. Now, step 1, when we check assumptions and write hypotheses, Each case appears in only one cell. Again, all expected counts must be at least 5. The formula for computing an expected count is slightly different for the chi-square test of independence because now we have 2 variables that we're looking at. The expected cell count here is going to be equal to the row total times the column total divided by the overall sample size. When writing hypotheses, the null hypothesis is that there is not a relationship between the 2 variables in the population. The alternative is that there is a relationship between the 2 variables in the population. Step 2, compute the test statistic. These are the formulas that we're going to be using. The chi-square test statistic formula is the same one that we saw with the goodness of fit test, and the expected cell value formula is the one that we just saw in step 1. Step 3, determine the p-value. We'll go to Minitab Express and we'll construct a chi-square distribution. The degrees of freedom for the test of independence is equal to the number of rows minus 1 times the number of columns minus 1. Step 4, make a decision. We'll look at the p-value and we'll compare that to the standard alpha level of 0.05. If p is greater than 0.05, we fail to reject the null. If p is less than or equal to 0.05, we reject the null. And step 5, make a real-world conclusion. Let's look at an example. Is there a relationship between gender and favorite winter sport? Data were collected from a sample of Stat 200 students, and here we have a 2-way contingency table displaying our data. Step 1, check assumptions and write hypotheses. Each case appears in only one cell. This assumption is met because each student was asked to check their gender and they had to choose between women and men, and they were asked to select their favorite winter sport, and they were only allowed to select one of the following: curling, figure skating, or ice hockey. The second assumption is that all expected counts must be at least 5. We'll go through and we'll compute an expected count for each of the 6 inner cells. We'll start with the first cell, women and curling. The expected count is equal to the row total of 288 times the column total of 41 divided by the total sample size of 520. Expected counts are often displayed in the contingency table after the observed count in parentheses. Let's look at the next cell, women and figure skating. We have the row total of 288 times the column total of 178 divided by the overall total of 520. Again, we'll store that expected count in the contingency table in parentheses after the observed count. We'll go on and we'll do this for all of the remaining cells. For women in ice hockey, and then the last row, men and curling, men and figure skating, and men and ice hockey. All of our expected counts are at least 5, so this last assumption has been met. We can conduct a chi-square test of independence. Our null hypothesis is that there is not a relationship between gender and favorite winter sport in this population. The alternative hypothesis, there is a relationship between gender and favorite winter sport in this population. Step 2, compute the test statistic. To compute the test statistic, we need the observed and expected counts. We have all of these in our contingency table here. We'll go through this procedure of observed minus expected squared divided by expected for each of these 6 cells. If we start with the women and curling cell, the observed count minus the expected count squared divided by the expected count. Women in figure skating, women in ice hockey, men and curling, men and figure skating, and men and ice hockey, we get a chi-square test statistic of 126.417. In step 3, we determine the p-value. We're going to go to Minitab Express, and we'll construct a chi-square distribution. The degrees of freedom will be the number of rows minus 1 times the number of columns minus 1. We had 2 rows and 3 columns, so we have 2 degrees of freedom. We'll go to Statistics, Probability, Distribution Plot to display a probability. We have a chi-square distribution with 2 degrees of freedom. We have a test statistic of 126.417. This is a very large test statistic, so we have a very small p-value. Minitab Express will say that p equals 0. We're actually going to write this as p is less than 0.001. Step 4, we make a conclusion. Our p-value is very small. It was less than 0.05, so we reject the null hypothesis. In step 5, state a real-world conclusion. There is evidence of a relationship between gender and favorite winter sport in the population of STAT 200 students. Next, I want to run through this example again using Minitab Express. First, I'll enter the data in as summarized data in our worksheet. We'll run through it that way, and then I'll also show you how you can do this if you have the raw data. In our worksheet, I'll put gender in the first column. We had women and men, and then across the top, curling, figure skating, and ice hockey. There were 14 women who preferred curling, 159 who preferred figure skating, and 115 who preferred ice hockey. For men, there were 27 who preferred curling, 19 who preferred figure skating, and 186 who preferred ice hockey. Now we'll go to statistics, tables, cross-tabulation, and chi-square. We have summarized data in a two-way table that we just entered. The columns containing the table are the curling, figure skating, and ice hockey. And the row labels are in that first gender column. We have to click over to display now to check chi-square test for association. I also recommend always checking the expected cell counts. That'll give you all of those expected values. It's really quick to look at it just to confirm that they're all at least 5. Here we have our output. First, Minitab Express gives us a contingency table. In each cell, the first value is the observed count and the second value is the expected count. Again, we can just confirm that all of those expected counts are at least 5. In the second table then, we have our chi-square test statistic. Because all of the expected counts were at least 5, we said that we could use the chi-square distribution. That is the first row here. We're going to be using the Pearson chi-square row. We will not be using the likelihood ratio row in this course. In our case, our chi-square test statistic was 126.42 with 2 degrees of freedom and a p-value less than 0.0001. These results are exactly the same as the ones that we just got when we ran through this by hand. Last example I want to show you uses raw data. I have these data here in a full Minitab table already. Again, I'll go to statistics, table, cross-tabulation, and chi-square. And now I do have raw data. We're looking at biological sex and winter sport. Again, I'll click over to display to make sure I get that chi-square test for association and the expected counts. Results should be exactly the same as what we got when we entered the data in. First, we have our contingency table with the counts and expected counts, and our Pearson chi-square test statistic of 126.42 with 2 degrees of freedom and a p-value less than 0.0001. The last learning objective is a relatively quick one. We'll calculate and interpret relative risk. Let's start with a quick review of risk. You saw this earlier in the course. Risk is essentially the proportion or probability. It's the number with the outcome divided by the total number. Quick example. In a sample of 100 girls, 6 met the diagnostic criteria for ADHD. To compute the risk for girls, we take 6, so the number with the outcome, divided by 100, the total number, and we get a risk of 0.06. Relative risk then compares the risks for two groups. So the risk in group 1 divided by the risk in group 2. Let's compute the relative risk of meeting the criteria for ADHD in boys and girls. On the last slide, we computed the risk in girls to be 0.06. In a sample of 80 boys, 10 met the diagnostic criteria for ADHD. The risk in boys then is 10 over 80, which equals 0.125. The relative risk, if we're comparing boys to girls, will be the risk in boys over the risk in girls. 0.125 divided by 0.06 gives us a relative risk of 2.083. To interpret this, I would say that boys are 2.083 times more likely than girls to meet the criteria for being diagnosed with ADHD. In other words, boys are more than twice as likely as girls to meet the diagnostic criteria. This concludes the full video lecture on chi-square tests. In this video, we covered the 4 learning objectives in this lesson. And here I have summarized all of the formulas that we covered in this lesson. Note that those chi-square test statistic formulas for the goodness of fit test and the test of independence are identical. The expected count formulas are different. We also looked at relative risk. As always, if you have any questions after watching this video, please post them to the discussion board on Canvas.